Thanks a lot, Gabe, for this wonderful introduction and also for the invitation to present here. Yeah. So indeed, I'm going to talk about AI, and it is Halloween, so you're the best dressed audience I've ever had. I feel underdressed, or shall I say, I came disguised as a European scientist. And if AI stealing your job as a geologist is not spooky enough, oh, let's see. This should do it. All right. Happy Halloween, everyone. Yeah. So this is indeed part of the eCore Distinguished Lecture Series. So they're paying basically for the trip. This is now the infomercial section of the presentation. They want me to talk a little bit about what eCore is and what they're up about. So eCore is the European Consortium for Ocean Drilling. And some of you might be aware of the history of ocean drilling, which really started with Project Mohole here in the US, which then gave rise to the Deep Sea Drilling Project, DSDP, with a ship, the Global Challenger that no longer is. And then in 1985, this transitioned to a new program known as ODP, the Ocean Drilling Program. That's when I met the drilling program. And that's with a very special ship for a lot of us, the JODIS Resolution, pictured here. And then ODP eventually became, in 2003, the International Ocean Drilling Program, IODP. And the big difference between IODP and ODP is in IODP, you had three major partners, the US with NSF, the Europeans with eCore, and the Japanese with MEXT. So very different drilling platform, as you can see, a very large research vessel from Japan, a riser drilling vessel, and mission-specific platform from the Europeans. So now, IODP is known as IODP Phase 1 up to 2013. Then it became IODP Phase 2 in 2014. So it still is IODP, but now it's called the International Ocean Discovery Program because drilling is a dirty word associated with some industries. But the important point here on this slide is that you can see that by the end of 2024, in fact, in September of this year, IODP is no more. IODP Phase 2 is terminated. And so there's a big question, of course, of what comes next. And that's when it gets a little bit complicated. The good news from a European and Japanese point of view is that there is still a program. It's known as IODP Cube. So we revert to International Ocean Drilling Program. Drilling is no longer a dirty word, apparently. So what is IODP Cube, or what is the situation now after September 2024? So you still have a consortium called IODP or IODP Cube that's headed by eCore, so that's the European consortium that has mission-specific platform. That means that whenever there is enough money, they will hire a platform that can be from any industry and go and drill some research. That's typically every 18 to 24 months cycle. And then the Japanese have the Chikyu, which is a very large, very costly vessel that typically operates for scientific research once or twice a year and does industry work aside from that. What happens with the US? There's a big question mark. The JODIS Resolution is going to retirement. It's actually, I didn't point it out, but the front slide was the last time I saw the ship, which was in Amsterdam in August, because I used to work for IODP for the US program. It was known as USIO back then. And so all the former staff were invited to see the JODIS Resolution one last time. Right now, it's effectively in Norway, in cold stack, they call it. So they basically just wait to see what will happen with the ship. There's probably going to be a program by NSF. It's probably going to be a mission-specific program as well, but some of you might know more about this than I do. And China is also very interested in bringing their own resources to the program. So you can see the situation is a little bit more complicated. In terms of IODP Cube, the key members I already mentioned are JAMSTEC, the Japanese program, and eCore. But there's also associate members such as Australia, New Zealand, and IODP India. And of course, NSF could join. They would be very welcome if they wanted to join the IODP Cube or any other partners, even temporary members. What can you expect from IODP Cube? And I guarantee you this is the last slide on the infomercial. is less deep water, riserless drilling as well done with the JOIDUS resolution. So those typical long core for pelisonography are becoming more difficult to get. More flexibility in the operation. That's a keyword to say that we have different platforms. There is this program, I think Gabe and I were talking about this, the Spark program, which essentially has seed, oh no, it's actually with you, Pete, which has seed money for you to go remeasure some existing cores. And that can be in any of the repository around the world, so Japan, US, and Europe. And US partners are welcome on a Spark project, though I do think it has to be led by either Europe or Japan. And there's a hope for cooperation amongst programs, so including NSF and IODP Cube. And there's also this thing called the Scientific Drilling Forum, where all this expertise can be shared. Right, infomercial finished. Let's go now to my talk. So I already mentioned that I used to work on the JOIDUS resolution. So I'm a marine geologist. That was, by the way, the best office ever. The view was unbeatable. But I'm also a field geologist. I've done, actually, since joining Imperial in 2008, a ton of work in Oman, in the desert. You have a few examples here on this slide. And yet today I'm here to talk about AI, and I've moved very recently, about 11 months ago, to Queen Mary into the, we call it DERI, the Digital Environment Research Institute, which is a multidisciplinary research institute that basically works on applied AI and applied digital research. And I had at this place there data science for the environment and sustainability. So what's the link between these two things? Well, one thing I've learned from being a staff scientist and working in the field is that observation for geologists are very important. It's the basis of a lot of what we're doing, but also that we're not very good at it, okay? And don't take my word for it. Take the word of this paper. So I'm a carbonate sedimentologist by training. So what I'm going to present today mostly revolve around carbonate sedimentology. So this is a thin section of a carbonate rock. And it's actually an artificial thin section, although we didn't know it at the time. So it's been completely built by Stephen Lockyer and his student Janabi in 2015. And what they've done with these thin sections, they have about 20 of them. They've sent them around the world to about 168 experts in carbonates, including my lab. Okay, so guilty as charged. Because they're artificial, they know exactly the Dunham texture, which is what we're using to describe carbonate rocks. So this one, for instance, as the one example, is a waxstone thin section. And then they asked us two very simple questions based on these thin section images. First question is, what's the name of this rock? Second question is, how hard is it to describe this rock? Okay. And the answer that came back, so again, for all the thin section, it's the same, but let's look just at this one, clearly is not very good. Because for that one thin section, I think there's something like 16 or 18 different names. Some of them are variation of waxstone, which is the correct terminology. Most of them are completely wrong. They're not the right rock, okay? Now, what's worse is if you look at how, yes. Oh, no. They made a fake rock. This is epoxy resin, and these are real carbonate grains in it. Good question, yeah. Okay, so the worst bit is if you look at how hard we found this rock to describe, not hard at all. So not only we're wrong, but we're also super confident about our description. And that actually resonated with me because I've experienced this also as a staff scientist on the ship, where we had to redescribe cores over and over again because they were inconsistently described. So that really triggered my interest in using AI to see if we could actually mitigate some of those human descriptive bias. So I've done, since then, a lot of work on artificial intelligence. Gabe mentioned, I started actually this around 2017 in earnest. I read a lot about it between 2015 and 2017, and then started with a master's project. We work on lots of things, seismic data, we work on satellite data, we do surrogate models, but today I'm going to focus more on cores and specifically on these 4 projects to show you different aspects of applied artificial intelligence to the geosciences. And no, AI is not going to replace you, but AI is going to become, hopefully I can convince you, a very useful tool for geologists to use. So let's start with the problem of describing thin section, or in my case, carbonate cores. But before we do this, just to make sure that we're all on the same page, we're going to be talking about deep learning. So let's introduce the topic of deep learning. We'll start with a very simple algorithm, the artificial neuron. So what's an artificial neuron? Well, it's an algorithm where you have some inputs. You pair those inputs with weights, so numbers. Those weights are trainable, so you learn those weights from the data. And then you have two functions. The first function is called the transfer function. It's a very simple function. All it does is you multiply your input by your weights, and you add a bias. So it's a linear model, right? The problem with this is that if it's a linear model and you combine millions of linear models, you obtain a simple linear model. Okay, so linear models are not very interesting if you have nonlinear problems. So the magic of the artificial neuron is the activation function. And that kind of emulates a little bit the way neurons fire or do not fire based on a threshold. Okay. So I show you at the top, two famous activation functions, but there's a lot of other ones. So the sigmoid function and the ReLU function. And the important bit is to realize that these are nonlinear functions. So depending on the value coming out of the transfer function, either you're going to output the value, or you're not going to output the value, or you're going to modify the value. So you obtain now a nonlinear building block. And if you combine nonlinear building block together, you can get a very complex algorithm. So this is really state of the art? Well, no, not really. This was published in 1943. So it's been around for a very long time. In fact, much longer than some of the statistical machine learning algorithm. Frigging is more recent than the artificial neuron, okay? So why is deep learning now such a hot topic? Well, even though it's been around since the 40s, first of all, it was not digital at the time, but nevertheless, the principle is the same. There are things that have changed. And what has changed is our ability to train neural networks that are much deeper than just one single layer. So now we have the algorithm backpropagation that allows us to build deep neural network. So lots and lots of these connections in different layers, which means that we obtain very complex algorithm that can be kind of a universal approximator for anything, really, including images, which is the topic we're going to talk about today. Right? That's the first thing. The second thing is the compute power that we have today is vastly superior than in 1943, or even vastly superior than in the mid-90s, okay? That's the second thing that really has changed. And the availability of framework, easy to use framework to do deep learning. And the third thing is the availability of data, okay? There's now a lot of data that we can access. In this case, data from the ocean drilling program. And the data I'm going to talk about come from two locations. So we're focusing today on carbonates. So in the very top, bottom right corner here, you have my favorite part of the world, the Marion Plateau, which has multiple legs in mycene carbonates. And then IODP 359 is actually the Maldives. So these are more recent carbonates. So I'm going to be using throughout my talk rocks coming from these two locations. So let's focus then on, can we use neural network to predict Dunham textures? Okay, and this talk is going to be pretty light on math and pretty light on like detailed architecture. So I'm going to introduce here the CNN, or the convolutional neural network, because they are really a backbone of computer vision. They still are today a backbone of computer vision. And the way they work, the important thing to realize is that they contain two parts. So in the first part, you have a series of convolutional filters that have trainable weight. So that's why we can use them in deep learning. And the role of these convolutional filters is to learn features from images, okay? So we can learn features from images, and then we flatten those images here on the gray layer. That's called the flatten layer. And then we have a second part of that network, which is effectively a fully connected, a standard neural network that does the classification, if you're doing a classification task. So one problem you may have heard about deep learning is that it requires a lot of data. And it can be very problematic to have a lot of data. And this is true. But one thing we've pioneered with my student in geosciences is this idea of using transfer learning. So what is transfer learning? Well, we're going to take the view that images are images. It doesn't matter if your image is a cat, a car, a dog, or a wax stone. Okay, it's an image. So essentially, the features that we get out of the images of a network that has been pre-trained, we can then use in the second part of the network, right? And the second part of the network, we then use our own data, which is images of carbonate cores, and we train our classifier, but we extract the information from this from the cores by the first part. So that's transfer learning, where we don't retrain the entire neural network. We only train the classifier at the end, and if you want to be technical, a few of the layers of the first part. Okay. Now it's important to realize that we have a large data set that we've built of 100,000 images. That's pretty large, right? But compared to what this was trained on, ImageNet, that contains 56 million images, it's peanuts, right? So this is like a technique that we wanted to test. And we published a paper last year on this very topic. So what we did is we took these images from IODP. We created 3 different data sets, one with 7,000 images, one with 41K, and one with 100K images, because we wanted to look at the impact of data set size. And then we took a dozen architecture, well-known architecture of CNN that were pre-trained on ImageNet, and we retrained the classifier part, and we wanted to know which ones work best. And the conclusion is like Inception v3 came on top for a lot of these, for most of our data set, but I don't think that's necessarily the most important thing. So how well did it work? Well, to really understand how well it worked, let me introduce you to confusion matrix. And confusion hopefully is only in the name, okay? So what is a confusion matrix? Well, a confusion matrix is a double entry table. On a vertical axis here, you have the actual label of our test set. So these are rocks that were not used for the training. And so that's essentially the label that the humans gave to the test set. On the horizontal axis, you have the label that the train algorithm has predicted for that particular image, okay? Now, there's an important feature here, which is this diagonal. Because if you think about it, on this diagonal are the images where the actual label and the predicted label are the same. In other words, that's the only place where you'll find correct predictions. A confusion matrix is plotted as a heat map. The darker the blue, the more images you have. And you can immediately see that for our test set, the algorithm does very well. We have more than 90% of the images correctly predicted, okay? So that seems to be very nice and consistent, but the real question is, how do we humans compare? So luckily, we can take the Lockyer and Genebi study that used 168 humans to describe the same rocks, and we can plot them as confusion matrices and compare them to the AI algorithm. Okay, so that's how they look. There's 2 of them. The middle one is everybody, but we will also ask for our expertise level. So the right one is the expert, level 4 and 5, no difference. Subtle differences, but no big difference. You can immediately see that there is much more spread in the description, which we've seen on the first slide. This beautiful diagonal that we see on the left here kind of disappear on the right, and especially notice that the floatstone and rutstone are kind of like a random guess almost, because not everybody has the same definition for them. Even though the definition is very clear, not everybody applies those definitions very systematically, okay? So now I'm not suggesting here that our algorithm is unbiased. I think it is biased, right? I think it has the bias of the people who labeled those images, but it's consistent. I can deploy this algorithm everywhere around the world. I'll have the same result. I can compare the results. These human descriptions show a problem that many companies and many scientific communities know, that basically you compare apple and oranges when you have different describers. And so in that way, I think that AI can help us as a tool for us to interpret our data. But I'm not here to, we're amongst friends. So I'm not here to just show you the good stuff. I want to also show you where there are problems. So let's be critical about our data set, and let's look at where we have the highest rate of error. So it's on the floatstone, okay? Floatstone, I have about 13% of them misclassified. Now you might say, well, we know that floatstone and rutstone are difficult because they're kind of similar, except that the roadstone does very well, 91%. So clearly this is not where the problem is. The other thing is, any carbonate sedimentologists in the room? Ah, there's one. You will have noticed the boundstone is missing, right? So we have one member of the class that's really not represented. And I can explain both of these things by just looking at our training data set. Okay, so here you have, again, for reference, the Dunham classification. And this pie chart shows the proportion or the amount of training images that we had. And if you look at this triangle here, these are our minority class. They're the ones that are less represented. Boundstone, we have only about 4,000 images, 3.5 thousand images. So we gave up. We said this one we can't really put in our first paper because we will not work. And floatstones, well, we have less floatstone than other rocks. That's why it performs poorly. So having a balanced data set and having enough data is really important. So now we're going to switch gear a little bit, and we'll see how we can correct for that. And for this, we'll use another approach, which is generative AI, your chat GPT, but for cores, okay? Right, so what we wanted to do, and this is something that's now in review, so not yet published, but hopefully soon, is we took our smallest data set. So this one's perfectly balanced. We have 7 classes of 1,000 images per class. And of course, we have a baseline model. So we train a model on those 7,000 images. And in fact, it's the same model that I showed you before. It's our Inception V3 CNN that performed the best. And we will use Inception V3 CNN, the exact same model, for all of the data sets here. Then we do what is known as traditional data augmentation. It's something that's been around now for decades that allows you to build from the original 7,000 images a data set of 168,000 images. So how do we do this? Well, for us, all of these images are the same, but for a computer, they're not. So here's the original image. All of the other ones are a variation from this image that we can obtain by, for instance, changing the brightness of the image or the contrast of the image, that's the second row, or we can do basically transformation that are geometric transformation, like flipping down the image, doing a reflection, doing a rotation. In the end, we have the same rock, so it's the same label, it's still the same Dunham texture, but for a computer vision algorithm, they look different. And then the last thing we did, so here we get 168,000 images, is we use this synthetic data generation. So this is this generative AI approach. Note that here, because it's a little bit more costly, traditional augmentation is very quick, you can do it on the fly. Here we only generated 22,400 images, okay? So how did we do it? So to explain what we did, I have to introduce this framework known as the GAN, or Generative Adversarial Network. In particular, we use the style GAN2 if you're really curious, but that's not the most important thing. So a GAN, it was really a revolution in deep learning when it was introduced. And it's a framework because it's more than one network. It's 2 networks. Effectively, we have a generator network. So the role of the generator, as its name implies, is to generate something, in our case, an image of a core, and it's going to generate this out of random noise, okay? Now, the first image is going to be random, but luckily we have the second network, which is the discriminator. Now, the discriminator's job is to determine whether the image it receives is real or a fake. And it will receive images from the synthetic generated cores and randomly also some real data images. Okay, so it's going to compare the statistical distribution of these 2 populations and determine whether it's a real image or a fake image. That's why it's called an adversarial framework, because the two networks actually compete. There's going to be an error in the end. Someone's going to be wrong. That error is known as the loss in deep learning. And if the loss is because the discriminator guessed correctly, then the loss is attributed to the generator. So in other words, the error is backpropagated through the generator, which means that in the next iteration, it's going to be better because it knows where it made its error. But of course, if the discriminator made the error, it gets backpropagated the error to its own structure. So you can see that because we do this iteratively through many epochs, in the end, we get a very good generator. and we get a very good discriminator. And depending on what your task is, you might be wanting one or the other. We want the generator, but if you're into detecting fake, you want the discriminator. So how good exactly is it? So let's look at this. This is actually real core images, okay, of the 7 textures of the Dunham classification. And now what I'm going to do is I'm going to generate images that are statistically very close from those example images, right? These are cores that do not exist. These are purely synthetic, but they're really hard to distinguish from the real thing. And yet they're completely different from the real thing. None of these images are exactly the same as the top column, okay? So that's how we can use generative AI to create synthetic data for training. So the real question is, does it actually make a difference? Well, let's find out, right? So what we're going to do now is we need metrics to determine how well the algorithm performs. So I'm going to use sensitivity and specificity. Exactly what they are is not so important. It's basically the probability of a positive result condition, or knowing that the sample is positive, and that's the reverse, basically the probability of a negative result, so it's not being from that class, if we know it's not from that class. But the most important thing is that higher is better for both of these metrics. So our baseline is the 7,000 images. So you can see that both of these metrics are in the mid-60s. And now the traditional augmentation with 160,000 images, of course, we're going to have a bump in performance. So we're now in the lower 70s. So the real question is, we've now trained with only 22,400 images. So much less than almost a factor of 4 or 5 less than the traditional augmentation. Are we going to be able to get a similar bump in performance? The answer is no. We get better, okay? Even though we use less images, we get a much better performance on the test set. So the question is why? Because less images is a good thing. It's much faster to train a neural network. And I think the answer to why we get such a bump in performance with synthetic data is that when you do traditional augmentation, in the end, you stay very close from the original image. So your variance in your training data is limited. With the synthetic data, we're actually increasing that variance. So we make our algorithm much more able to handle unseen samples. Okay. So, determining the Dunham texture of a rock is cool, but it has its limitation, right? We're also interested, at least those of us who are carbonate sedimentologists, are interested in grains. So you see here an example of a rock and the different grains that you can see in the rocks. And this is really kind of it's really time consuming if you want to quantify grains or forms or whatever. So really a question is, can we actually use deep learning to quantify grains in pores, right? And for this, we'll use object detection, which is a well-known technology in deep learning. And we've actually trained a detector based on about a dozen different classes of grains, okay? You can see that the vast majority are forams because they're small, so you find a lot of them. But we also have red algae, non-skeletal components, serpulid, only 1%, so we have a very unequal distribution of our different classes. So as always, we like to compare technologies. So we've used 2 different technologies to see which one worked the best. So we used the most recent one, YOLO. YOLO for you only look once, not live once, okay? You only look once because it's a one-stage detector. What does that mean? It means that the CNN, this is CNN based, will determine where there is an object and what it is in one operation, okay? There's also an older technology, slower, although ironically called faster RCNN, okay? It's faster than the original RCNN. And this is a 2-stage detector, meaning there's 2 CNN inside. One first determines what the region of interest are, so where is there a grain? And the second one determines what that grain is. So it's 2 operations, so it's slower. So we train both of these algorithms. And now on a test set, we can look at how well they perform. So here what you see is on the vertical axis, precision. So in other words, it's a percentage of time when the algorithm tells you, say, it's a forum. How often is it correct that it's actually a forum? And on the horizontal axis, it's just the classes, okay? So we plot the different grain classes here on the horizontal axis. In red, you have the performance of faster RCNN. In blue, the performance of YOLO. And also in this box, you have the average performance. So let's look at that first. So it's true, YOLO V5 is an order of magnitude faster than faster RCNN. But faster RCNN, the slow horse, at 600 milliseconds per image is still faster than my best PhD student and certainly faster than me, okay? So everything's relative. So when you're training an algorithm to do self-driving, these latency issues can matter. When you're a geologist, I will argue it doesn't matter. What's more important is to see the performance of the algorithm. And there, actually, the older technology, faster RCNN, has a head start because it's 73% more, or the precision is 73% versus 59% for YOLO V5. Okay, so just on average, it's better. But if you look grain by grain, it's always better. You can see that the red dots always, or the red diamond, always plot on top of the blue dots. And it's not so important for the large fossils. You can see that faster RCNN is in the 90% precision, whereas YOLO is between 70 to 85, okay? But it's much more acute for smaller grain, like, for instance, forams or aggregates. You can see that that faster RCNN is 50 to 60%, which means that when it tells you it's a foram, it's 50 to 60% of the time correct, whereas YOLO V5 is only 1 time out of 3 correct when it tells you it's one of these classes. Smaller grains are harder to categorize because you have less pixels to make that determination, okay? So therefore, we concluded that using faster RCNN was the way to go here. And that's maybe a lesson here for everybody. You know, the shiny new toy is not always the best toy. So you really have to use or train and test all the algorithm on your particular data set. So the question you might ask is, how well does that perform against humans? So luckily, the reason we chose that case study is we have 2 wells or holes, 1196A and B, that are part of our test set. We didn't use this data for the training. And a friend of mine, Gilles Coneza, did some quantification and published back in 2005. So we have his data, and we can compare his data to our own AI-generated point counting. So I'll start by being a bit cheaty and showing you my best performing grains, right? So those are the ones where I have more than 70% precision. So let's have a look at the comparison between AI and human classification. So in blue, you have our ML estimate. In orange here, you have the Conesa et al. Study for the entire well. So it's about 350 meters. And there are some difference, but overall, I would argue that the trends are all captured, okay? So with machine learning, we capture those trends. Now, one thing I don't show you on this first slide is the level of description. So here you have 100% of the data collected by the humans, but you only have a fraction of the data collected by the machine learning algorithm. Because when I put all the data we have, it looks like this, right? And if you want to see even more closely, notice here the white and the black. Black is when we have recovery. White is when we don't have recovery. That's going to be important for the next part of the talk. So we could focus on one core, which has actually only about 3 meters recovery. And we can compare the description that we did with ML versus human description. So you can see for 2 data points, we have about, I don't know, 20, 30 data points, okay? And you can see they show very interesting, nice trends, right? So they don't seem to be completely random, and hopefully I'll convince you of that in a couple of slides. So why is this important? Well, because if you look at what we've done with this case study, is we've actually described 12,000 small images, right? That have a resolution of 3.2 centimeters. So it's like a human describing a core at 3.2 centimeter resolution, all right? So of course, this took time. How long did it take for our algorithm to do this? About 3.5 hours, okay? Just about enough for a French lunch, right? So how long would it take for a human? Now, these are admittedly some European estimates, right? Because it's 1 minute per image, 8 hours working per day. They're also non-academic estimates, and 5 days per week, definitely non-academic estimates. But if you take this into consideration, I come up with the conclusion that you need about 5 weeks of a geologist describing these scores. 5 weeks versus 3.5 hours, and we have all the trends in 3.5 hours. Much, much, much faster. So let me try now to convince you that indeed we capture those trends and that it's consistent. So to do this, what I'm showing you, remember we have these two wells? What I didn't tell you is that they're about 50 meters apart. So really they should be very similar, okay? So of course we have lots of areas where we don't have cores, so that's why you have gaps. But you have site 1196A here, site 1196B in the middle panel. And on the right panel, it's the grain. So this is skeletal grain and the two wells plotted on top of one another, okay? And now I'm gonna show you all the data, not just the ones we do well at, but all the data. It's gonna be animated, so it's gonna go quick. I just want you to look at the trends between the two wells to see if we're systematically getting the same trends for all the different grains. And we kind of are, okay? So this opens up the possibility, if you're into lithostratigraphic correlation, I don't know why you would be, but if you were, you could actually now start using grain size counting for cheap, because that didn't take us a long time once the algorithm was trained to basically compare rocks that are close by, right? But we still have this problem of the lack of recovery. And this is really an acute problem, especially in carbonates, but not just in carbonates, right? So you see here for these two wells in particular, we have, I was a PhD student on the ship when we were drilling there. It was depressing, right? Because you get only like a meter for every 10 meters you drill. This is not great recovery. Luckily, the ocean drilling program can also do logging. So in particular, we can use this tool that is known as the FMS, or the Formation Microscanner. And logging is great when it works because you get a continuous record of the geology as you log down in the well. Now, the FMS is really looking at the resistivity of the rock. Okay, so you have this tool that has the pads, 4 pads, with actually a good, a decent resolution, I think 16 millimeter resolution, so that's not bad at all. And it produces, these 4 pads produce images of the well bore, okay, resistivity of the rock, but that resistivity of the rock tells you something about the geology. So here you see it, you see the 4 pads, and you see the geology. Now, it's great, but it's also problematic because me as a geologist, you know, I cannot interpret this. And I know for a fact that people in industry who are geologists cannot interpret this, so they actually ask service company to tell them what's the rock, okay? So that's a problem. It's a barrier of entry in terms of the interpretation. Even if you're an expert, though, you can only interpret this at the relatively large scale, right? So you can find fractures, you can find faults, you can find things. But if I give you a tiny bit of it, you cannot tell me what the Dunham texture of it is, right? So the last part of this talk really is exploring if whether or not AI can be used for image translation. So in other words, take this image of a resistivity of the borehole and transform it into that, which is a synthetic core image. And we'll see whether or not this actually works and makes a difference for geoscientists. So that's a whole PhD, by the way. So, but I only have, I know I'm short on time, so I only have a few slides. And the technology we use is, again, the GAN technology, which I think for synthetic image works really well for scientific, generative AI. It works really well because the architecture we use is known as Pix2Pix HD, and it's a supervised approach, meaning that we have we don't just input random noise, we actually input the FMS data that corresponds to the core we want to generate. And so through this process and many years of sweat and tears from my student Syra, we got some results. This is our final results. So that's the paper that's now finally in review. So what are you looking at? Well, you're looking at the end product, of course. Under the yellow arrow is the actual core. So this is real rock. Under the blue arrows, and you have 3 examples here, these are synthetic rocks that were generated from the FMS data. Okay, so you're looking at these 3 cores. You can see the wax stone and the grainstone look remarkably similar. They're not the same, and that's normal because that's a statistical approach, right? It's not really just a translation from the rock, but they look very similar. And actually also the last rock, which is a rudstone, looks quite similar, but I will point out, and that is going to be important later, this big grain here, I know with the light we don't see it very well, but that's a large rhodolite. And actually, if you look at the core in detail, you can see the generated core kind of shows a ghost of something like a rhodolite, but the rhodolite is not really there. And that's because what I've not told you is that the image we generate is not a full core. Okay, we generate small thumbs. So I'm showing you here how we generated the thumbs for that particular rock, and then we stack them together to form the image. And you can see that the rhodolite is larger than the images we generate. So we have here already a problem that we can't really generate these images very well. I have a postdoc working on this now. So there's work in the make, so to speak. But the real question is, will this actually make a difference? You know, okay, this is cool, but does it make a difference for real geology, right? Well, okay, we can test this. So we can test this on humans. And since I'm a PI, I have, willing PhD students that can actually do core descriptions for us. And so what we did with Saira is we gave 25 images of the real cores to my research group. They're trained to describe carbonate rocks. And we asked them to define the Dunham texture of those rocks. Now, you're expert in confusion matrices, so you can see they're doing fairly well. The average accuracy is 87%. And yeah, you can see this beautiful diagonal again. So mostly they did the correct prediction on real core images. Great. I did my job. I trained them well. Now we gave them the same size thumbs of FMS data. That's how it looks, right? So good luck. What's the Dunham texture of this one? Yeah, exactly. I can't tell, and clearly neither can my group. Okay, this is their confusion matrix. Average accuracy 14% for 5 classes, because we didn't have all the classes here. We had enough paired images for the 5 classes you see on this slide. 14% means it's a random guess, right? And fair enough, at this scale, FMS data is not, you cannot interpret it. You cannot tell me what the Dunham texture is. So the real interesting thing is to do this. Use our generative AI approach to generate the synthetic images of those very same FMS data. And then again, ask the group. And by the way, they didn't know which one was real, which one was synthetic. We also asked them to tell us if they thought it was real or synthetic. And yeah, tell us what the Dunham texture of this synthetic, you don't know what synthetic core is. And because we have the label, we can compare this to the real label. And you can see immediately that their accuracy bumps back up to 73%. Way, way better than straight from the FMS data. Not as good from the real cores, but we know why. Because if you look at where their errors are, it's systematically under-interpreting the coarse texture as a finer texture. And that's because we do not do a good job at really representing the large grains. Okay, so we understand where the error is, and that's something that we can work on in the future. We have a project with Japanese colleagues in the Sea of Japan looking at using this technology for paleoceanography. Right, so that brings me to my conclusions. Okay, so I hope I've convinced you that AI can actually increase productivity. It's not here to replace you. It's here to do the boring job for you and do it fast, okay? So it increases our ability to describe things at much higher resolution or to do things much faster. It's not just faster, it also is increasing our accuracy, okay? Some of the algorithm I showed you, this is an academic project, they're probably biased, but as a community, we could get unbiased algorithm if we have like a statistical description of course, for instance, right? Then we know there's been paper that show that if you ask a population to describe things, it's a Gaussian distribution and the real label will be in the middle. So we could retrain on a much better label data set. And that means that then we have a tool that allows us to be more systematic in the way we describe things. But also, I hope I've convinced you that generative AI is not just a toy. It's not just ChatGPT, even though ChatGPT can be useful. It's also very useful for scientific application. In particular, I think this idea of domain translation, where you take something from a domain that's hard to interpret, like an FMS data, and transform it into something that's familiar to your target population, i.e. geologists and core images, you really increase the ability of humans to basically use the data. So even though if you don't want to use AI to make the description for you, you can use AI as a way to generate a data set that you're more comfortable to interpret. And I've showed you that this actually increases the performance of the people. And finally, because this is an eCore talk, I want to talk a little bit about the importance of IODP. The role of IODP, data is really king when it comes to doing AI and machine learning. And there is a ton of data from the legacy from DSDP all the way to IODP, with even more data being generated in papers as we speak. So I think this is a really big role here to play. So let me finish with a few thanks to my PhD student, my collaborators, eCore and IODP, of course, but also my funders for this research. And thank you for your attention. Oh, all right. I think you were first. Yeah. Yes. Yes. Yeah. No, this is a great question, and we worked on it over the summer with a master's project. Yeah, I thought exactly the same way, because really what you're saying is that those classification are bins. They're bins for essentially the amount of mud, but also whether the grains touch or not, and what's the size distribution of those grains. And so we've started to look at using object detection to determine grain size and proportion of grains. And you can, I'm convinced you can actually do this. So I didn't have time, but if you're interested, I can show you on my computer the results of the master's project. But yeah, we get some decent distribution of grain sizes, and then we can bin these grain sizes into the Dunham texture. There are complications. So the bound stone is one, because it doesn't depend on the proportion of grains. But yeah, we absolutely can do this, and I think we should, because it's moving us away from essentially human limitation in terms of how we can perceive the world into a more quantitative way of describing things. Yeah. Yes. Yes. Correct. Correct. Ideally, what you want is you want to know what it is, what's its shape, and what's its size. Yeah. Great. Thank you. Yes. Yeah. 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 Uh, Yes, you're absolutely right. So the answer is yes and yes. Yes, you need to retrain. But yes, in theory, you could do like an Uber algorithm that's capable of handling different camera resolution, different sensor types. One thing you didn't mention, which is actually even more important for carbonates, is the age of the carbonates you're describing. So, that carbonates are basically a reflection of the skeletal grains living at the time of deposition of the rock. So a Neoproterozoic carbonate looks very different to a Mesozoic carbonate, looks very different from, Miocene carbonates I showed you, and to a recent carbonates, right? So we have this issue, and in fact, we played with this. We train on Miocene carbonates, and then we generated texture on recent carbonates, or more recent carbonates, Pleistocene carbonates from the Maldives. And we got what we expected, which is we got these beautiful rhodalgal carbonates that were not correct, because that's the training data set. So it's the training distribution. So we don't have rhodalgal carbonates in the Maldives. But what was interesting was that the texture was correct. So the information on the texture was correct, even though the image was incorrect. So yes, so right now at this stage, you'd have to retrain for every location, and this is, time consuming. How would you get around this? So with the problem of the data, it's about data quantity. We would need much more paired images from carbonates from all around the world so that we actually represent truly the distribution of what carbonates look like, for instance. And substitute whatever rocks or whatever data you have in mind to carbonates here. For the sensor, then I think maybe it's a little bit an easier problem because this is something that is already done in image detection. You have cameras of different make, different resolution, and you can still recognize a fish in it or the object. So that is something that is a little easier to sort. But again, you'd want to have different range of quality of data in your training set, which is not the case here. We have medium to good FMS data, and we have very good for images because it's all coming from IODP. Yeah, you're welcome. Yes. Yeah, so originally, yes, but the ones we generate are lower resolution. Yeah, yeah. So that comes from the framework that we use, that Pix2Pix HD. HD stands for what it means. And basically, with this framework, you're able to do what is known as super resolution. So you really you go, if you want to be a little technical, what you do is you go into what is known as the latent space, which is a really compressed representation of your image. And then you decode that latent space. So the latent space is created, in our case, from the FMS image, and then you decode it into an image. And in the process of decoding, there are technologies we can use to improve the resolution. And of course, because we train the algorithm and we do the loss at the end with the final image, we use MSE, so mean squared error for the loss. If your upscaling is of bad quality, that will impact the score. So you will propagate the error. So you end up getting good approximation of how the image should look in high resolution or higher resolution. That's a good question. Yes. Mm-hmm. No, you just feed images into this. And an image, is basically a tensor, so kind of like a multidimensional matrix. In the case of an image, the dimension of your tensor is n by m, which is the number of pixels you have in your image, times 3, because we have RGB image, so you have 3 channels. So that's what goes into the algorithm. Where the description comes in is as the label. So you first have to determine what the thing is, because this is supervised. Just a single world, yeah, just a single world. Although you're not limited to a single world, because really the way the training is done under the hood is your word is transformed into a label 0, 1, 2, 3, 4, right? So you could get a whole sentence if you wanted. Yes, I think I had a question back then. I'll come back to you right now. Yes. Yeah. Yeah. So you're right. So that's this whole thing that deep learning algorithms are kind of black box, and they're black boxy. Yeah, it's true. Because when you have millions of parameters, it's kind of hard to know why the decision was made that this is a particular Dunham texture. You cannot get around this completely, but there are ways where you can mitigate this problem. So we've done some of that, and it's in our paper, where you can actually look at feature maps. So at each stage in your neural network, you can look at the parts of the image that are more important for the determination of the final class. And so sometimes you can see whether your algorithm actually uses noise or wrong information to come to the right conclusion, or whether it uses some like true information. So we've done that, for instance, on satellite images where we had dunes, and we could clearly see the crest of the dune, and kind of like what you would expect as a geologist being spotted by the algorithm. So that gives you a little bit of confidence, even though you don't explain how it works. It gives you a little bit of confidence that it kind of works nicely. but it doesn't prevent the fact that it's kind of like still a bit of a black box. So as long as you don't have like a legal requirement to explain how you reach your decision, I'm comfortable with this. There are ways which we didn't use in those algorithms. There are ways in which you can calibrate your algorithm. It's quite complicated. You cannot just use out-of-the-box method, but we're doing this now for our Mars detector, where we try to determine the mineralogy. And what does it mean to have a calibrated algorithm? It means that, you know, here I'm showing you the class, but really under the hood, what you get is a probability of your sample belonging to a certain class. Now, in theory, if an algorithm tells you that it has 90% probability of being of that class A, then that means that 90% of the time when it tells you it's from class A, it should be from class A. In standard deep learning, that's not the case. You tend to have probabilities that go, you know, it's either 0.2 or it's either 0.9, right? And nothing in between, right? And so you can train algorithm to basically be calibrated and give you a realistic probability of your sample belonging to a certain class, which then means that you can, again, humans in the loop, you can look at the probability distribution and spot the ones where you're like, oh, you're telling me it's this class, but really you're like 55% sure, you know? So it gives you a little bit more control on that. That's a long roundabout way to answer your question, but hopefully that answers it. Okay, good. And Brenda.
Sold. This is amazing.
Yeah.
How is that going to be accessible to general geoscience?
That's a great question. So one of the things I'm passionate about is to try to make these tools available for people to use online, right? So in theory, when you train an algorithm, if you're a company, if you're Microsoft, right, you can deploy it like ChatGPT on a server somewhere, and people can come and, you know, upload images or do something like this. So that's the plan. The problem is that there's a cost associated with the plan, right? So it's not free to have machine learning models running and making inferences. So that part I've not figured out, but I think this is the way forward. I think the risk, it's not necessarily your question, but I'll take it towards the risk. The risk is that this becomes a corporation. You know, this becomes Google cores, and then you have to pay, you know, 20 pounds a month or dollars a month subscription, right, to get your carbonate description done. I'd rather avoid this if possible. Yeah. I would also say that what I've presented to you, I would not feel comfortable like putting out there and saying, guys, use it, this is perfect. Because no, it's not. It's, again, academic project, proof of concept. We know how to do a really good algorithm, but we'd need more time, more data, and it should be a community effort.
Good place to add 20 pounds a month and
Okay. Thank you. Gabe, I'm just gonna keep it real. It's not gonna write the paper. Yeah, that's for ChatGPT.